Hello everyone. On this video we will be going over partial derivatives. Alright, so let's start off with our definition. Okay, so if we let z equal our function with variables x and y. Okay, the first partial derivative with respect to x and y are partial of f with respect to x and partial of f with respect to y, and defined by derivative with respect to x, xy, is equal to the limit f of x plus delta x, y, minus your f of xy over your delta x as your delta x approaches 0. Okay. On some books you may see as age or some other variable, same thing. And your partial with respect to y, that should be a smaller y, of with x and y variables is equal to the limit of f of x, y plus delta y minus f of xy all over delta x. And that's as your change in y approaches 0. Okay. And of course, this is all assuming that the limits exist. Alright, now if you're going to solve for your partial derivative, there is a process to it. Okay, so if you're trying to find your partial with respect to x, so to find your partial with respect to x, you treat all other variables as a constant. So you treat all other variables as a constant, and you will strictly differentiate with respect to x. Differentiate with respect to x. Okay. And same thing for the partial with respect to y. To find your partial with respect to y, you would treat all other variables as a constant and differentiate with respect to y. Okay, so you have pretty much the same technique for both. It's just a difference between which variable you're going to differentiate by. Okay, so if you are still writing, feel free to press pause. We're going to go ahead and move on to our next page. Okay, so here we're going to look at our partial derivative notation. Okay, so again, we're going to say that our z is equal to function of x and y. The partial derivative with respect to x and with respect to y are denoted by, okay, so let's start off with our partial with respect to x. You may see it as the partial with respect to x, xy. You may see it as the partial derivative with respect to x of f of xy. You may see it as the partial of f with respect to x. You may see it as the partial derivative of z with respect to x. Or you might even see z sub x. Okay. Same thing with partial derivative with respect to y. You may see it as partial with respect to y, xy. You may see it as the partial with respect to y of f of xy. You may see it as the partial of f with respect to y, partial of z with respect to y, or either z sub y. Okay, all of those mean the exact same thing. This whole row represents partial derivatives with respect to x, and this whole row means the partial derivative with respect to y. Okay. Now, if you want to evaluate at a specific point, you just plug in those values. Okay, so the partial derivatives evaluated at a point, we'll call them x sub 0 and y sub 0, are, okay, you may see it as partial derivative of z with respect to x, or you might see f, and that's at x0, y0. That's the same as saying partial with respect to x, but you're going to plug in those two values. And the partial with respect to y at x0, y0 is f of y at those points. Okay, and again, this is just if you're going to plug in numerical values. All right. Okay. So what a partial derivative does is it tells you the slope of a three-dimensional function at a specific point and what direction that slope is going in. Okay, so let's say you want to see it visually. We draw our three-dimensional graph where we have our x, our y, and our z. Okay, so let's say if we have a object, or an object here, in 3 dimensions. Okay, so let's say this object is just floating in the air. Okay, and we have a value of x. We'll call that x0. A value of y, we'll call that y0. So when you meet those two up, of course that point is your x0, y0. Again, x0 could be 3, y0 could be 8. So this would just be a point 3 and 8. Okay, so when we take that up to our 3rd dimension, okay, this point will tell us the slope in the direction of our x-axis. At that point. Okay. Now, same thing with the y-axis. We draw our x, y, and z axis. And let's say if we have, again, just drawing our any random object in 3 dimensions. Okay, so this is an object just floating in the air. Okay, again, let's say this is our x0, our y0, put that out there. Okay, which means that this point here would be our x0, y0. But if we went up to this point on the graph, the slope in the direction of the y-axis would be our partial derivative with respect to y. Okay, so all in all, our f of x is equal to slope at x0, y0, f of x0, y0, and the direction of x. And this graph, our partial with respect to y, is equal to the slope at x0, y0, f of x0, y0, in the direction of y. Okay, so geometrically, that is what you will have. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our first example. Oops. All right. So for example, what if we wanted to find partial with respect to x and the partial with respect to y for f of xy is equal to 2x minus 3y plus 5. Okay, so just rewriting our function is 2x minus 3y plus 5. So our partial with respect to x is just the partial with respect to x of 2x minus our partial with respect to x of 3y plus our partial with respect to x of 5. Alright. Now remember, when you're finding the derivative with respect to x, every other variable becomes a constant. Okay, so that means your partial with respect to x will equal the derivative of 2x with respect to x is just 2. Okay, so that becomes 2 minus the derivative with respect to x. You have a 3 and a y. So because it's the derivative with respect to x, both the 3 and the y are seen as constants. Okay, so you have the derivative of a constant is just 0. So that disappears. Same thing here. The derivative of a constant is just 0, so that disappears. So we know our partial with respect to x is equal to 2. Okay, so let's try the partial with respect to y. Okay, so your partial with respect to y is equal to the partial with respect to y of 2x minus the partial with respect to y of 3y plus the partial with respect to y of 5. Alright, so that means your partial with respect to y is equal to, remember, now it's the partial with respect to y. So you have 2 times x, really that's just a constant times a constant with respect to y. Okay, so the derivative of a constant is just 0. Okay, now the derivative with respect to y of 3y is just 3. Plus, the derivative with respect to anything of a constant is just 0. Okay, so our partial with respect to y is just equal to negative 3. Alright, so if you are still writing, feel free to, oh, actually we have enough room to do the next example on the same page. Save some paper. Alright, so what if we wanted to find partial with respect to x and the partial with respect to y for z is equal to natural log of x squared plus y squared. Okay, so to solve this one, first thing you want to do is remember that the derivative with respect to u of natural log of u is equal to u prime over u. And in this case, the u is x squared plus y squared. Okay, so to find our partial with respect to x, that's the same as saying the partial of z with respect to x. Okay, so that's going to equal, remember that's u prime over u, so that's the partial with respect to x of x squared plus y squared all over your x squared plus y squared. So it's u prime over u. And so if we take the derivative of both of those terms, the derivative of y squared with respect to x, remember, with respect to x, it treats the y as a constant. So the derivative of a constant is 0 here. The only one we really have to worry about is the derivative of the x squared. So that's just 2x. okay, over your x squared plus y squared. Of course, that is because partial with respect to x of y squared is equal to 0. Alright, so now our partial with respect to y, or partial z with respect to y, is equal to the partial with respect to y of x squared plus y squared, all over your x squared plus y squared. Okay. And again, we're going to find the partial derivative of both terms. Okay. Now, the partial derivative of x squared with respect to y, remember, it's with respect to y, so it's looking at the x squared as a constant. So the derivative of a constant is 0, and the partial with respect to y of y squared is 2y. So you have 2y over your x squared plus y squared. And of course, that is because the partial with respect to y of x squared is equal to 0. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay. So, for example, what if we wanted to find the slopes of the surface given by f of x, y equals negative x squared over 2 minus y squared plus 25 over 8 at the point 1/2, 1, 2 in the x and y directions. Okay, so really that's just a fancy way of saying the partial derivative of x and the partial derivative of y. The slope in the x direction and the slope in the y direction. Okay, so the first thing we're going to do is find our partial with respect to x. Okay, so that's going to equal the partial with respect to x of negative x squared over 2 minus the partial with respect to x of y squared plus the partial with respect to x of 25 over 8. Okay, so we can see here that the partial derivative with respect to x of y squared, again, is with respect to x, so that y is looked at as a constant. So the derivative of a constant is 0. And here, again, the derivative of a constant is 0. So that just leaves us with the partial derivative of negative x squared over 2, which is just negative x. Okay, so we have our first partial. Now for our second partial with respect to y, that's just the partial with respect to y of negative x squared over 2 minus the partial with respect to y of y squared plus the partial with respect to y of 25 over 8. Okay, again, this is with respect to y. So the x is considered a constant. So you have the derivative of a constant is 0. Again, here you have the derivative of a constant, so that's just 0. which leaves us with the derivative of y squared, which is 2y. So you have the minus 2y. So partial with respect to y is negative 2y. Okay, so we found our derivatives, so we just have to find them at the point 1/2, 1, and 2. So at the point 1/2, 1, 2, remember this is our x0, y0, and z0. Okay, so our partial with respect to x of x0, y0, in this case, is our partial with respect to x of 1/2, 1. Okay, so our partial with respect to x is just negative x. So the only thing we can plug in is the x value, which is 1/2. So that's going to be negative x. So that's negative 1/2, which is negative 1/2. And our partial with respect to y at that point, the partial with respect to y at 1/2 and 1. Okay, so the partial with respect to y is negative 2y. So we're just going to replace the y value. That's negative 2 times 1, which is negative 2. Okay, so we have our slope in the x direction. And we have our slope in the y direction. All right. So if you are still writing, feel free to press pause. We're going to go ahead and go on to our next example. All right, so for example, what if we wanted to find the slope of the surface of z equals e to the negative x cosine of y at the point 0, 0, 1 in the x and y direction. Alright, so what I want you to do is press pause and try to solve this one on your own. Alright, so assuming you've pressed pause and worked this one out, let's just verify your answer. Okay, so the partial with respect to x, just the partial with respect to x of e to the negative x cosine y. Okay, now in this case, the y factor is considered a constant, so we can just bring that out to the front. So you have cosine of y times the derivative with respect to x of e to the negative x. Okay, which is really just cosine of y times negative e to the negative x. Okay, so your partial with respect to x is equal to negative e to the negative x cosine of y. Okay, now our partial with respect to y is just the partial with respect to y of e to the negative x cosine of y. Okay. Now because we're finding the derivative with respect to y, the x factor is considered a constant. So we can just bring that out to the front. We have e to the negative x times the partial with respect to y of cosine y. Okay, derivative of cosine is negative sine, so we end up with e to the negative x times negative sine of y. Okay, so our partial with respect to y is equal to negative e to the negative x sine of y. Okay, so if we look at the point 0, 0, 1, where that's your x0, y0, and your z0, partial derivative of x at 0, 0, remember that's your x0 and y0, is negative e to the negative 0 cosine of 0. Okay. E to the power of 0 is just 1, so you have a negative 1. And cosine of 0 is just positive 1. So that's negative 1. So the slope in the x direction is negative 1. Your partial with respect to y of 0, 0 is equal to negative e to the negative 0 plus sine of 0. So it's your x0 and your y0. Okay, again, e to the negative 0 plus the negative there gives you negative 1. And sine of 0 is 0. So our slope at that point in the y direction is 0. Or in this case, just a horizontal line. Alright. So, hopefully this video made sense, and I will see you on the next video.